So once again, thank you guys for coming on time. I tried to do the Teams thing. Somehow it's having some conflict with my SIT account, and still unable to do that. But I've asked them for help already. Probably they will ask me. They'll update me in the next few days. But do let me know if it's fine to be on Zoom. Because later on we'll be using the breakout feature of Zoom, and it's a bit easier. So I think after the lecture on Tuesday, you will be a bit more aware of the style that I may adopt, which is during the class I'll try as much as possible to get more participation. I know it's tough, but we'll try. And the reason why I'm doing that is because I think it will really enhance your learning experience, and so together with us having some form of interaction, together with the breakout sessions of you interacting with your colleagues, right? Hopefully it will increase the way we learn and improve the way we learn. Okay, so back to the lectures. So last week, on Tuesday, we talked about, we were here talking about keys, foreign keys, and also integrity constraints. So we talked a little bit about key or candidate key. So maybe a little bit of recap before I jump right into the material. So last week we talked about relational algebra. There's maybe I'll just open this as well. What feature? Yeah, breakup. Yeah, yeah. So I'm sorry. So last week Tuesday we talked about tables. Talked about every table having a particular schema. So so the table column names, so maybe S1, S2, S3, S4. All these will fall under a certain schema. They may have certain attributes that they may require to take. And we talked about every single row in a table has got to be unique. So once we know that it was unique, then we talked about let's say if S1 is able to take values A, B, C, D, S2 is able to take values A and B, S3 is able to take values C and D, and S4 is able to take values of E. So we talked about what's the cardinality of this table. Is there a Wei Xiang here? Mr. Wei Xiang, are you around? Okay, so just a very quick question. So let's say we have this table with these four columns. What is the cardinality of this table? Four is not. Four would be how to say? 4 is the number of columns. We realize that in this S1, it can take 4 values. In S2, it can take 2 values. In S3, it can take 2 values, and in S4, it can take 1 value. So these are the number of possible values each column is able to take. And we know that the entire table must be unique. And so for it to be unique, every single thing must be different. So the number of possible values for me to fill this up will be 4 times 2 times 2 times 1, which is equals to 8, 16. Okay. So if you really want to calculate this out, this will be something similar to, if you really draw it out, so all of this will be E, because this can only take a value of E. So this will be A, B, C, D, A, B, C, D, and this will be A, B, A, B, A, B, C, D, C, D, C, D. Along that line. So every single row will be unique, and in total, this will be there there are altogether 16 possible values that this can take. So actually this shouldn't be EBP, but anyway, there are 16 possible values that yeah. So please sorry. What was I going to say? Yeah. So the cardinality of this will be 4 times 2 times 2 times 1, which is 16. So one point to take. I think please try to mute your speakers. I think it will make our lives a bit easier. Thank you. Actually, I tried to implement the waiting room, but I think it didn't work this time now. Yeah. So we were talking about this last Tuesday. So with this, then we the next thing that we want to talk about is that how then do we in fact identify a role uniquely? How do we identify the role uniquely? So yeah, how do we identify the role uniquely? And right now, what we have is that we call the set of so-called attributes within a table. If they are able to uniquely identify a role, we call it a key, or you can call it a super key. Okay. So it's a bit crowded here, so I'm going to. So last week, Tuesday, when we talked about this. So let's say if you have a table like this, and there is this ID 1, 2, 3, ID 4, 5, 6, 7, 8, 9. And this name, let's say this A, B, C. And we know that, but let's say there is a guy 5, 6, 7, also with name B. So we know that this is your unique ID. And your unique ID is able to identify you, of course, like uniquely. It's like your NRIC number is unique to you. So we know that based on this column alone, we will always be able to find out the exact role that you're looking for. So this is the principle of a key. But because ID is in my, it is one of the attributes that can be used to identify the entire role uniquely, I can also say that 4, 5, 6 B can also identify my role uniquely. So this is also a super key. Why? Because I already have this can identify me uniquely already. So just by definition alone, this can identify the entire role uniquely. So even if I have so-called funny characters like this, plus, minus, times, divide, right? And I have another, and this, everything here is also a super key. Why? Because I have one attribute here that is already that of a key. Okay, let's look at another example. This is, let's say this is the name. Is 自圈 around? Yes, yes, Mr. 自圈. Can I ask you, can I use name to be the key? Assuming unique. Okay, so yeah. I mean, yeah, your quantification is correct now. So if it's unique, yes. If it's unique, then of course you can use that as the key. But I think Mr. Jiang also said something correct. If it's unique, you can do it. but of course we don't recommend it too, because names are often repeated. So it's not unusual to have two people with or other people with the same names. So it's actually a real possibility of that happening. So in this situation, like in this table in particular, name cannot be used as a key. And the reason why and the reason why is that there are two people with the same names here immediately here. So immediately it can't be the key already. And Mr. Jiang has also another comment that primary keys are usually numerical. Yes and no. For example, our IC numbers can be considered as a key. So not necessarily is numerical. So it's not always the case. Although you can say that it is of more convenience to assign it to be numerical, but it is not not a criteria, not a criteria at least. But it's a good point, yeah. So we are here. So we talk about what the key is. So right now, earlier we said that this ID is my name, and this may be the symbol. This entire thing is a super key, because one of this is a key. So this entire thing is able to uniquely identify a particular role. So a candidate key is the minimal number of attributes that is able to uniquely identify a role. So in this situation, the candidate key is going to be ID. ID is going to be the candidate key, and only ID. If I have ID and name, this will not be able to be a candidate key because there is an extra attribute here, which is not required to uniquely identify my entire role. Okay. So let's I will illustrate with another example. So let's look at this example. So let's say in this case, like I'm merging two different data repositories, let's say, and both of them have a unique ID. So let's say I have school one, and this is school two. And in this school, I have 1, 2, 3, and over here, so I have 1, 2, 3. And this name and this name, let's say T. Okay, so it's one. But it happens that there is a ID 1, 2, 3 at each repository. So one thing that we do when we merge them, we can easily resolve this issue, right, by doing a 1, 2, 3 ID. And we can also add in another new category, which is school. So this is 1, 2, 3 from 1, and this 1, 2, 3 from 2. And in this situation, right, what do you think can ID be the candidate key? Is Mr. Marcus around? Yes, Mr. Marcus. Can ID alone be the candidate key? Is your yeah, good. May I ask why? Yes, it is not unique because there are two students there with the exact same ID. So Mr. Marcus, may I have a follow-up? What do you think a candidate key would be for this situation? Yeah, ID and school. So ID together with school, the two of them together will be the candidate key. So if school by itself will not be the candidate key, ID by itself will also not be the candidate key. So together, the two attributes put together will then become the actual candidate key. Okay. Okay. Good. Okay. Very good. So let's say if I have other fields here. So other fields, let's say I have major and I have a minor. And so I have a major here. And also I have a minor here. So ID, school, major, and minor, all of this together is going to be a super key. These two alone is going to be a candidate key. And this three alone is going to be a super key as well. And if I have just ID and major, these two is not a key. Okay. Yeah. So so this is just to let everybody be aware. Yeah. So this is what the entire slide is talking about. So the minimal super keys, whereby you have to cut down to you don't have any extra attributes anymore. That will then be the candidate key. Okay. Candidate key in this case contains let's say this is apply. It is actually a database of students applying to various universities and or rather various majors of universities. Excel, is it? Okay, I will consider the Excel. Okay, I will consider Excel. Thank you. Okay. Yeah. Okay, I'll consider that. Okay, let me try that later on. So in this situation, ID is not going to be a unique ID. It's not going to be unique because a student is able to apply for many different universities. So like student 1, 2, 3 actually applied to three universities. So Stanford, Berkeley, and Cornell. So SID by itself cannot be a candidate key. And SID with CNAME also cannot be a candidate key. Why? Because we have two Stanford applications there, because that student 1, 2, 3 applied for two majors in Stanford, both computer science and EE. So SID and CNAME together can't be a candidate key because it can't uniquely identify a major. A particular role. And what is required is that we need SID, CNAME, and major. And this would then be a candidate key. Because all these three put together will be able to uniquely identify any single role here. And SID, CNAME, major, and decision, this will be known as a, together, this will be a super. I was laughing earlier because I realized that I don't know why he put this guy to be rejected for Stanford and accepted for Berkeley. So it sounds a bit not very nice, but anyway, it is what it is. Yeah. So anyway, somehow the author decided to do that. But anyway, I digress. Yeah. So anyway, So we have we now know what are super keys, what are candidate keys, and now what are candidate keys? Yeah, and now the last one that we want to look for is a primary key. So for example, if let's say I have this database, so it is Is super key just yes, correct. Super key is just candidate key plus extra attribute. You also have to note that note that what else was it? Super key, a candidate key is also a super key, but the super key is not a candidate key. Okay, so and the super key can consist of multiple candidate keys as well. Yeah. Okay. So anyway, yeah, thank you for your question. So we have this table, and we have employer ID. Oh, wait, I was so let's try. Let's see if this is easy or not. So there's EMP name, and there's mobile. So let's say this employer 1, 2, 3, and this name and mobile 1, 2, 3, 4, 5, 6, 3, 4, 5, 5, 6, 7. So of course the mobile number is unique. Is unique. Has the mobile number has got to be unique, and the employer ID also has to be unique. So in this situation, right, we know that the both the employer ID and mobile will be unique, will be unique to every single employee. And so both this and this, they will be both considered to be candidate keys. So both of these rows will be able to use, both of these columns will be able to uniquely identify every single and any single row. So if I say I want to find the employee with phone number 345, I will know immediately that it is employee number 2. Employee number 2. If I want to find which is employee number 3, ID 3, I know immediately it's this gentleman over here. So both of these columns are you're able to uniquely identify any single row here. And the primary key will denote the candidate key that the database designer chose as the principal means of identifying which row it is in the relation. So for example, the database designer, right, has the flexibility of choosing either employee ID or mobile number to be the primary key. And so, but of course, usually they will choose employee ID to be the primary key. So yeah, and I'll go to that a little bit later. Yeah, so they will use the primary key to manage the tuples in the relationship. So when you do any searching or when you do any selection, they will use the so-called the primary key to be the main one to select. And so because of that, right, Mr. Is there a Muhammad Rasif? Are you here? Okay, never mind. How about Simon, Mr. Simon CEY? Are you here? Okay. Why do you think mobile is not a good choice for primary key? Okay. Okay. So you're assuming that okay, yeah, so okay, no, it's a good answer. Yeah, people change phone. Yeah, yes. Too much numbers is maybe possible. Too much numbers. Yeah, it's true. You may need country code. People change phone. Some people no phone. Yeah, these are all. Yeah, actually, these are very good reasons. Yeah. So people they change their phones. Sometimes they may have more than one mobile. So you may end up with one employee with the same employee with two mobile numbers. And they may be accidentally inserted into the database. And there's also one very important reason. So for example, let's say right, if you have this and you have this is just like, let's say this table, right, is a very generic, generic table. Then you have one that's very sensitive, which is like pay, and you have employee ID, and then you have pay. Rather, you have the key lah. It's actually should be called a foreign key, foreign key from your generic. It should be the foreign key from the generic table. So the key that's linking there. So if let's say this pay is 4,000. So let's say if this foreign key is an employee ID, then you are going to do a so-called, when you want to reference how much is this person taking, right? It is a little bit more natural, to do a so-called a query across two tables. So you're going to say from this guy, who how much is he drawing? I can do a direct I'll do a direct reference. Whereas if I use the mobile phone, right, then it may look the entire so-called thinking may be a little bit strange, because you're going to do a so-called a drawing based on the mobile number. Yeah, it's still possible, but it's a little bit strange. And as what Mr. Ryan says, right, if they change phone, then it's going to be very complicated. So if let's say this guy changed to a phone that is so let's say this guy changed first to 444, and this guy suddenly changed to let's say this guy changed to this number, and this guy changed to 123 suddenly. Somehow the number was recycled and it changed back, and this table wasn't properly updated. Then there'll be a lot of inconsistency within your database itself. Okay, so that's it. Yeah, so I was talking about foreign keys. So relationship R1 may include attributes from another table. So this is primarily why we do it. Actually, like this table that we see, right, is very, very common, that you have a so-called a foreign key that references another so-called key from this part. So typically, this will be a primary key of the other relationship. Typically, you'll be a foreign key of another table. Yeah. So for instance, in this table, Mr. Kenneth, will you be able to on your mic?
Yeah.
Yeah. The echo is quite bad. I actually wanted you to give a brief explanation of what these two tables are trying to say. I think that might is okay. It's okay. I think somehow I don't know why there's this echo here. So I think it's fine. I'm going to just explain it. So actually, this table is just talking about this database consists of two tables. The table names are students and applied. So students are the database of students with their student ID, their names, their current GPAs, and then I can't remember what's the meaning of this. Sorry. And then apply is going to be the college and the major and the result that the particular student applied for. So in this table, what it is trying to say is that Miss Amy has a GPA of 3.9 and she applied for 3 colleges. Out of the 3 colleges, she applied for 4 majors, and these are the 4 that you can see here. She was rejected for 3 of them, but she was accepted into Berkeley under their computer science program. Yeah. So this is what the entire this relationship is trying to say. Yeah, what this is trying to say. Yeah. So Anyway, if you are aware, if you may be aware, you're probably aware, Berkeley CS and Stanford CS, they are always calling with one another about who's better. And of course the general I will not comment more, but they're always having this rivalry over it's like NUS, NTU, this kind of rivalry. So anyway, that's why it's a bit funny. Anyway, so anyway, this is how you explain this entire relationship. And first, this SID is going to be referencing from the SID over here. Oh, my friends told me to call me. It's okay. No worries. No worries. So no worries. So data integrity then relates to the correctness and consistency of data that's been stored in the database. So there are several types: entity integrity, referential integrity, user-defined integrity. And I'm going to go through them one by one. So and entity integrity. So your primary key, in this case, SID is your primary key. So you cannot be null. Your SID can't be null. So there's a violation here. Okay, what I mean to say is that there's a violation here because I have now these two are supposedly the same people, but then I have a null value for my primary key over here. So this is my student table, and I have a null value over here. So this is a so-called a violation of the entire of this entity integrity thing. So your primary key cannot be null. Okay, next, referential integrity. So over here we have let's say we have another table. So earlier we have a students table of the table of all the students in the school, and then this is the table of all the places that the student applied for. So if there is a school that is so this is a foreign key. So this is probably I can't find my key. This is probably my primary key. So this will be referencing to this, and so every so-called attribute value, or the cell value here, must correspond to a value over here. It must correspond to a value over here. There is a violation here because DigiPen is not found over here. Okay? It's not found here, so there's this violation. It's a bit interesting in the sense of whereby there is a null value here, but some databases do not consider this to be a violation. I'm not sure why also, but for example, Marriott SQL, they don't consider this to be a violation, but they consider this to be a violation. Personally, I'm not sure why, but this is what happens. Maybe I'm not sure why. Maybe I'm not sure why. And the last one is referential integrity, whereby let's say if you set a certain attribute to go between a few values, and so say GPA must be between 0 to 4. Over here we have a violation here because this is above 4. So this is the last type of violation, which is referential integrity. Okay, so we come to the end of lecture number 2. So what we want to do now is following. So on your distance, I actually uploaded this set of slides, this exercise. Actually, I want you all to go into breakout rooms to discuss about this. So there's going to be, I think, 5 questions in total. So I will, the next 15 minutes, right, I will hover in between your various breakout rooms, and then you guys can go for a break from 9:20 to 9:30. We'll come back at 9:30 to go through these answers. But I really hope that you all will participate in the breakout rooms. Anyway, I will be I will be going in and out of the breakout room. So when I go in, hopefully there's some activity lah. Okay, so don't be silent or what lah. Yeah, just try to do it, and it will help lah. It will help. Okay, so I'm going to put you all in the breakout rooms now. I'm going to put about 5 to 6 into one. 4 to 5 into one. Okay, so please enter the rooms. I'll be joining the rooms one by one, and hopefully you'll participate there. If there are nothing else, I will see you at 9:30. Thank you. Okay, welcome back. The time now is 9:30, and then we will start. So I hope everybody had the discussion. I was in and out of the rooms. Happy to find that some rooms are very active, and I hope that this will be something that will be useful for everybody, so that I think discussion-wise, usually would be will promote more learning between one another. But anyway, let's go through the solution. Yeah. So the first one is find the tuple in S which violates referential. Is there a Mr. Ong Zian? How about Mr. Sean Chia? Yes. What do you think the answer is? Ong Zian is saying that the 2, 3. I don't know. It's SD23. Is it 2 and 3? Is it SD2 and 3? Okay. So both of them mentioned that it may be these two. So we'll go through them. So we talk about referential integrity. Of course we know that A over here, or rather we see that this is the primary key, and for table R, for table I, for table S, this is the primary key, and A is the foreign key. We know that every value here of the foreign key must correspond to a primary key over from the original table. So we have 2, which is over here. So this, okay. We do the easy one first, and we have 1 here. 1, there's 1 here. So this seems to be fine. So this is number 3. There is no 3 here. So definitely this would violate referential integrity. So this is definitely one of the issues there. The other one would be this now. So intuitively speaking, null values would seem to violate referential integrity because we can't find a null reference here. But however, in most implementations, they allow null values in your foreign key. So in most implementations like Maria, SQL, and such, this is in fact acceptable. So this is not a referential integrity in this case. Okay, so here there's only 1. Look at the second one. Which relation does not violate integrity? Is there a Shurash? Are you there? Yes. Which one do you think does not violate integrity? D. May I ask why? Yeah, great. Very good. So the primary key needs to be unique. So okay. So before that, sorry. This relationship. Thank you so much, Mr. Shiraj. This relationship R, and we know that primary key is equals to 8. So the primary key needs to be unique. So immediately we know that this can't be it because we have these to be the same. We also know that the primary key cannot be null. I think my team. Okay, good. Good to hear that the breakout rooms are somewhat working. Yeah. So anyway, this is now, and so this can be done because primary key cannot be now as well. Okay, let's look at this. For this, the primary key is fine, but B then is the issue. Why? Because B must be an integer, and this is a floating number, and so this will be incorrect as well. So the only one that's possible is going to be D, whereby A is an integer and it's a primary key. B is only integers. And so C is integer, but now values they are somewhat acceptable. So this is also fine. Okay, so this is how we solve this question. Okay, let's look at this one. Is there a Ejon? Ejon, are you here? Yeah, hello. What do you think the cardinality of this is? Of this table is? Yes, correct. Very good. So it's 2 times 2 times 3. So which is equals to 12. Very good. Yeah. So this is the cardinality of this table. So it's so if you really want to visualize this, this would be something like maybe John. Fiona, me, Tom, and Jerry. So there are 12 guys, 12 possible. So you can actually consider it to be like this. And then I'm going to probably have maybe check this. Something like this, and then let's hope this let's hope this works. Something along this line, but something along this line whereby every single line will be unique. I may have some numbers incorrect here, but yeah, I may have something, but something along this line whereby every single line is going to have a unique permutation of these so-called characteristics. Yeah, but the number is going to be 12 ultimately. Okay. So the foreign key of this relationship, is there a derping? Yes. What do you think the foreign key of treatment is? Yes. PID. Yeah. Yeah. So it's typically PID. Yeah. So assume that this is the primary key. This is going to be the foreign key. Okay. Very good. The last one, choose the valid tuple in the relationship. Let me see who I can ask. There was this gentleman. Is there Amir? Is it Amir? Are you here? Or did I get your name incorrectly?
Yes, hello.
Yes, yes.
Hey.
You mind explaining to the class this question?
Like which one's correct or?
Yo. Which one is the valid tuple? And why not the others?
So the valid one is the first one, the 100, 101, now 10. The other common answer that people will put is the second one, the child's 50, but 50 Because if you look at the teams, there's only 2 teams there with a team ID of 10 and 20, and 50 is not part of it.
Mm. And then Justin, the reason is incorrect is because this one.
Because MID is the primary key, so can't be null. Then for the last one, the primary key, the MID is beyond the domain stated.
Very good, very good, very good, very good. Thank you so much, Mr. Amir. Yeah, so I think he had many good points. So yeah, so for those reasons that he stated, right? Yeah, so all these will be invalid, and there'll be only this one that's going to be valid. Thank you. Very good, very good. Yes, Mr. Harry says, wow, nice. Okay, so anyway, very good. So we come to the end of this part. So I'm going to go to the next part of sharing. Not sharing, sorry, of the lecture. So don't need this already. This, what is this? Don't need this as well. So this we go to lecture number 3. Okay. So we are now in lecture number 3, which is relational algebra. This is a heavy topic, so we go through this. We go through this together. Hey, sorry, Prof. The sequence. The sequence of the tuple. What do you mean? Sequence of the tuple does not. Okay. Sequence of the tuple does not matter. The sequence of where it comes, is it? The sequence of it, the name, okay. So maybe I try to I'm not sure what your question is, but the sequence of this. The sequence of this is important. Okay, the sequence of this and this is important because the first one is going to refer to your ID, second one is going to refer to your name, and the third one is going to be your team ID. So the sequence of these three is important. Yeah. If that's what you are asking. If you're asking if the sequence of which one comes first or not, then it's not important. So basically, if you have let's hope this one will work. Basically, if you have if you have let's say if I have 1, 2, 3 and no, regardless of the order of this, it wouldn't matter. It wouldn't matter. Okay, so why I'm saying that the sequence of this is important, right, is because I have placed out the schema here in this manner. So of course, you can say that if I have a member, MID, team ID, and M name, and if I have this, and I have something like this, these two are actually equivalent. So the sequence of the so-called the columns does not matter in that certain aspect. However, it is because we have we specify the schema of this to be in particular this one. We have specified the schema, or rather we have specified the exact schema of this so-called particular row. If we switch over the tuples in this manner, we have to specify again the new schema of this. And in our aspect, right, although these two is totally equivalent, but then if you were to present this in this manner, right, then this one will mean something else. This one will actually mean that the name of this row is equals to 10, and his team ID, right, is equals to now. Good. Okay, that's good. Okay, let's go on to the next part. Okay, so in relational algebra. Okay. So relational algebra is important because all the queries that we do get translated to relational algebra, and then they get optimized by they get optimized. So it is a formal language based on operations. Every operator accepts one or two relation instances. These are just theory, which I don't want to repeat because no meaning. Yeah. So not no meaning, so rather very hard to visualize. Yeah, very hard to visualize. So this is actually a relational algebraic statement. So what this is the SQL. This SQL query. I'm going to select the name and the salary from my table, and this is the condition. So maybe maybe it is probably the case whereby I will have this table of name, and I have a salary, and the table name is employee. So I'm going to select, and maybe there's some other things, but doesn't really matter. So because I'm only selecting the name and the salary from my table called employee, where my salary is below a certain amount, which is the condition. So as I was saying, this entire query gets translated into relational algebra. So these are the two examples of relational algebra in the blue boxes. Let's look at a easier one to see, which is this one. So I'm going to, this is a so-called a selection of my salary less than a certain amount from my table employee. So this is actually this part. I'm selecting roles in my employee table with a salary of less than 50,000. And that's the first part. And the second part is I'm going to, this is called a projection. Project only my name and my salary. So there may be other tables here. For example, maybe address, bank account, maybe other things like gender. There may be other things, but we don't need in this query. We don't care about those items. We only care about two things, which is the name and the salary. Which is why we only project out the name and the salary over here. So this entire relational algebraic statement is translated, or rather is obtained from this SQL query. Okay, let's look at the second query up here. So in this second query, we are projecting the name and the salary from my employee table, and from then on, we want to select the salary less than 50,000. So this is another representation of this query. They will both give the equivalent results. But as we will find out later on during the course, one query will be more preferred than the other. More preferred in the sense whereby it will make my query more effective to be executed. Yeah. So basically that's why we are studying relational algebra. So we have a SQL statement over here, and then they get translated into relational algebra, which are the two statements that you see here on top. Okay. So some of the operations that are there, we have union, intersection, the difference, the product. We also have so these are just the typical operations. I think that's division of the join, operations on relations, selection, projection, join. I'll go through this in more detail as we go along today. So again, we have projection, which is this. We have selection, which is this. Okay, so we are sorry, before that, so I'll go through each one of them now. So first will be union. So R union to S is the instance whereby it contains all the tuples that occur in either R or S or both. So in this we have R and S. When we do union, they must first be union compatible, meaning that they must have the same number of attributes and they must have the same domains. So if you want to recall what we mean by the same domains, right, it means that they must have the same type. And let's say if this is from A all the way to H, this must also be from A all the way to H. Rather, it must allow for values from A all the way to H. So this is what it means by having the same domains. So when we have R union with S, what we will have is then we have a new table. We have a new table here, and I will be having. Let's just keep. Let's say that we take the values column names from the second. And this will be A, B, C, A, D, G, F, B, E, A, B, E, and H, D, G. So what do you notice about this? In this case, right, you notice that whenever we do the union, this and this, they are the same. And so when we do the union, it doesn't get repeated. This and this, they're also the same. So when we do union, again, it doesn't get repeated. And the main reason why it is so is that, right, we call that in this so-called, we call this somewhat like a view, which is like a table, but it is a result of a query. In the same way, right, every single in this case must also be unique. So in this union, all the tuples here must be unique. And so we remove off all the items that are non-unique. Okay? Yeah. So I correct myself a little bit. It's not always the case that the view has non-duplicate items. So I wasn't very correct to say that. But in this operation of union, the output of it is non-duplicated. So this is why we see that some of the items here the duplicated items are actually removed. Okay, good. Yeah, let's look at so we're going through this already. Let's look at the next one. So we have a union of girls union with the boys. This one should be quite simple. So what we will have is we'll just have another 4003, 4005, and Bob drawn here. Yeah, so that's all. So this is just. No, it does not. Very good question, Mr. Ryan. The order of the lines do not matter. So the order of the in general, right? In general, the orders of the rows do not matter in DB. Why? Because we always carry out a lot of operations to sort them according to certain attributes. So in a certain sense, the ordering of these lines, right, or these rows, they do not matter. Yeah. So that's a good question. So So this is just the result. Okay. So intersection. So intersection is it will contain the items that have both R and S. So actually it's quite intuitive. So these two are similar because both R and S. So intersect. Yeah. So R, S, and this A, B, C, A, D, G. So there will be F, E, E, and this will be all the rest of the other two. A, D, G, and H, D, G. Okay. So yeah, so you can imagine it to be like a Venn diagram, and this will be what it looks like. So intersection of these two, there's this 401 has symbol, 404 symbol, and so intersection over here. Okay. So difference again, all requires to be union compatible. So the attributes, so they must have the same number of attributes and they must have the same domain. So when you have R minus S, so this will be this minus of that which is over here. So we have A, B, C. So this will be deleted away, and you will get this. So the interesting thing about the difference is that R minus S is not equals to S minus R, because if you remove S minus R, you would remove away this one, and you'll be left with these two rows, which gets populated down. So so that is not it's not the same as R minus S is not equals to S minus R. Okay, so something for you to think of. So if you have a student and database, if you want to do this minus this, I'm going to end up with 4002. And if you have, let's say, if you have REG CPP minus REG DB, you're gonna end up with 4003 and 4005. So basically, this is present there, so you're going to remove it, and 404 is also present there. So you're going to remove these two, so you're going to end up with excuse me, 403 and 405. Okay, so Cartesian. Okay, am I going too fast? I think it should be okay, right? These are quite okay. So Cartesian product will return all the instance containing why this slide is incorrect. It should be here. Cartesian product has all the instance of R followed by all the fields of S. So R times S. So this will be what R times S looks like. So how do we get this? Is because, sorry, I'll correct this slide later on. So how do we get this? Is that we have R, which is A1, B2, and then we also have S, which is A, B, B, C. Let's do this. I'm going to use Excel. So I have A1, and I'm going to have B2, and I'm going to have A, B, B, then ABB, C, and I have 10, 20, and 10, and this is A, B, B. Yeah. So we are going to have a Cartesian product of these two tables. So what's going to happen is that I'm going to have this. Is this clear? This R and this S, and this A, B, C, D. Is this clear? I hope this is clear. What I'm actually doing is just reproducing what we see over here. Yeah, so I hope this is clear. So if I have R times S, right? R times S, what's going to happen is that I will need to have A, B, C, D, E. Okay, so this is R times S. This is S. Find my merge. Yeah, so this is going to be my R. This is my S. This is my R times S. So I will have A and 1. And I will have to multiply it with all the values over here. So I'm going to have this like this. And I'm going to have B and 2. And multiply with all my values over here. So this is going to be my R times S. Okay. Okay. So what I'm saying is that every single row here, we can multiply with all the rows over here. So that's why this row here gets multiplied with all the rows over here. This row here gets multiplied with all the rows over here. So that's why I have A1 with all A10A, B10A, yeah, all we can see all here. And this row gets multiplied with all the different rows here. All okay with this? Okay, let's look at what will S times R look like. So you have S times R, you have C, D, E, A, B. C, D, A, B will look like this. So let's look at this. So okay, I'm going to do this now because okay. Let me look. So let's say look at this row first. This row will get multiplied with both rows here, so it will look like this. Okay? So this row we can multiply with both rows here, and then the next thing will be this row will be multiplied by both rows here. And you see the pattern that emerges, right? Will be multiplied by both rows here, and this last row will be multiplied by both rows here. So this will be the result of S times R. Okay, so am I making sense so far? Okay, so the interesting thing comes in. These two are equivalent. Yeah, so R times S is equals to S times R. So as what was being asked, right, we just need to reorder the rows and the columns, and you'll find that they are exactly the same. So for Cartesian product, S times R will be directly equals to R times S. Yeah, I hope that is clear. Okay, let's look at the, so we have example. So how many tuples are there? Will there be in student times course? Okay, let's ask somebody. Is there a Mr. Yu Xuan? Yu Xuan or Yu Xuan? Yes, sir. May I know what do you think the answer to this will be? Yes, very good. It's going to be 15 because I have 5 rows here. I have 3 rows here. So the Cartesian product will be 15. And the total number of columns will be equals to 6. 1, 2, 3, 4, 5, 6. So student times course will be equals to number 15. All clear with how we got number 15? Okay, if nobody wants me, okay, let's go ahead. Okay, so now we are at selection. So selection, you select a subset of rows from a certain relationship. So as what we have done so far, right? When we talk about relational SQL query, we've been talking a lot about selecting this from something where something equals to something. Yeah, so this selection will usually come with a certain condition. So earlier we have a salary less than 50,000 as a condition. Of course, we can have other conditions. In this case, right, it is where A2 is equals to A or A2 equals to B. So in this case, we are how we read it is that we are selecting all the rows where either A2 is equals to A or A2 is equals to B. So in this original table, we have A2 where I have this and I have this. So I'm selecting these two rows out. Okay. And in this case, how we read it is that I'm selecting all the rows from table R, whereby A3 is going to be greater than 0. So I only have two, which is this and this. Oh, so it's the same. So so this will be here, and this will be here. So if I happen to have a sigma where A3 less than 0 of R, I will have A1, A2, A3, and AD minus 4. Okay, so this is the query of sigma of A3 less than 0. And the schema of the result is going to be the same as the schema of input. Why? Because we actually didn't do any other actions other than selecting. So I'm going to be selecting all the attributes of the when my rows hit a certain condition. So the schema that will be the result is going to be the schema of the input. Okay. So oh yeah, before I continue, remember to mark your attendance. Yeah, before I end, sorry, remember to mark your attendance because only 4 more minutes before the attendance thing closes. Yeah, so I'm going to go on to this last point. Then yeah. So return the students who are not in the above relationship, where SID less than 4003. So these are the students whereby SID is greater than or equals to 4003. So what this is trying to ask is that, can I give me the students where SID is greater or equal to 4003. Yeah, so sorry, there's a double negative here. Yeah, so it's not in this, so it's actually greater than or equals to 4003. So in this aspect, we are looking at a selection of the students whereby my SID is greater than or equals to 4003. Okay. Did I make a mistake here? Okay, I don't know why this is here, but let me check on this. Let me check on this later on. Maybe I made some mistake here. Okay, anyway, I have 2 more minutes. I don't think I want to go into this one now. Yeah, so I'll check on this slide whether did I make a mistake here or not. But before before we end off the session today, are there any questions that I can help to answer? Oh, okay. Okay, let me see if did I make a mistake or not. I have 2 more minutes, so while you're waiting for questions, right? I'll see if I make mistake. Who are not in the above relationship. Oh, I think it should be like this. No idea. I think it should be like this. I think what I mean is like this. Yeah. So this one will be correct. So So yeah, I have 1 minute to clarify. So return SID greater than or equals than 403. So this will be it. This will be students with SID greater than or equals to 403. And this will be the students who are not in the above relationship. Yeah, so I interpreted this wrongly. So it's not in what it means to say is not in here. So that's why there's this not in here. So I think the wording is not very nice. Yeah. So yeah. So I think I should rephrase this because you notice that I confused myself earlier as well. So it's actually not in this one. So I have a not operator here. Okay, good. Okay, at least we cleared that up. The comparison operator is still wrong. Is it wrong? I think it's okay then. I think it's okay. I think it's fine. Maybe Mr. Ryan, which part you think is incorrect? Oh, Mr. Wei Hing also say should be not. Oh, no. As I say, this wording is very bad. So what this is asking is not in this relationship, and what so this wording is actually asking this. So the wording of it is really bad. It's really bad. So it's actually asking who are not in this above relationship, which means SID less than 4003. Yeah, so the wording of this has got to be improved. So maybe yeah. So maybe not in the relationship, which means yeah SID. So this is what it means lah. Yeah, this is what it means lah. So the wording of it is it's quite bad. I'm sorry about it. Yeah, I will do this. But but there's another not outside. Yeah. So there's this less than 403 is equals to this lah. So these two are equivalent lah. So not not SID is actually equivalent to SID less than 4003. So these two are equivalent. Yeah. The wording is not very good, so I apologize for that. Yeah. So this will be a better way to word it. Okay. Yeah, seems okay. I hope everybody. Do you need me to clarify this again, or is everybody are we all agreeable that this is okay? Good. Okay. Very good. Okay. Then in that case, the time is 10:15. Sorry, time 10:12. Sorry, there's a little bit of overrun. Then what I want to say is thank you so much for your time this evening. Hope that you guys learn something this evening. We'll try to continue to have this kind of arrangement, and hopefully with the breakout classes it will enhance the learning. And yeah, thank you all for today. I'll upload this video onto YouTube later on this evening. Anyway, thank you so much, and have a good evening. Good night. I'll hold on for a while here in case any one of you have any questions, and you all want to yeah, most welcome. Bye. Good night. Bye. Good night. Welcome.